started the research last summer when he won one of the summer research assistantships in the department. And his path to the success was much like roller coasting. We had a great success last summer, and so we felt like, back to the beginning of this semester, well, you should be able to finish everything in 2 weeks. Then, as you know, life sometimes doesn't go your way. Nothing really worked for many weeks. So he was very, very frustrated. And I kept encouraging him, that's life, right? I mean, if everything works so well, you would be able to get your PhD in 3 years or maybe 6 months. So after really 10 or maybe 11 weeks, we finally discovered what went wrong. And so today he's going to really share his story and his discovery. So here's Shane.
Thank you all for coming. So my research for basically the last year has been into condensed magnetic storage with my advisor, Dr. Hometown Shi. So the overview of my work was we started with fabricating aluminum nanotubes using a multi-step anodization process, which we really kind of hammered out the recipe over summer. And so after you fabricate these nanopores, which is, here's an image right here, the aluminum is put right here, and then you grow these oxides, or the oxide, up into these pores. You want to analyze these types of samples using something that has really high magnification, such as a scanning electron microscope, which we have here on campus located in the Keck Lab on the second floor of Salazar. After we analyzed these samples and found that we had a really highly ordered array of nanopores, we wanted to work on reducing this barrier layer here down on the bottom of this image right here. The barrier layer is really just this connection in between where the aluminum and the oxide starts growing. The reason why we want to thin the barrier layer is because we want to increase the pore diameter of these samples and reduce this layer here without actually removing the entire thing. It's important for us to do this because we want to eventually electrodeposited nickel nanowires into these pores using an alternating current pulse. Obviously, as Dr. Shi mentioned, there was a lot of troubleshooting a part of this process. Everything doesn't quite go as planned as you would like to hope. And here's just a little metric just to tell you how small nanopores are. 1 nanometer is basically 10 to the negative 9 meters. So why would you want to fabricate these highly ordered nanopores and insert nickel nanowires? Well, they have potential use in condensed magnetic memories and storage. They have uses in single electron devices, and they also can be used in optical media. Here's a general overview of how these samples are created. You're going to do an anodization process, which usually after the first anodization you will have these pores, but they're not very symmetric and they're not very highly ordered. So what we want to do after that is you want to do an intermediate etching with a very strong acid, which will dissolve the oxide and leave basically this like mask, we call it, on top of the aluminum, which then allows us to perform further anodizations, which increases the order and the symmetry of these pores because now they are pretty symmetric and they stand upright. After we are happy with the order of our samples, we then would move into the barrier layer thinning process. And then when we are happy with the increase in diameter size and decrease in resistance of the samples, we would deposit the nickel using that alternating current pulse. This is an example image of what the surface of this aluminum would look like after the multi-step anodization. It's on a 2 centimeter by 2 centimeter aluminum sheet, and the aluminum is extremely pure, 99.9996% pure aluminum. We use a 0.3 molar oxalic acid, which is an organic acid for our anodization electrolyte, and we use chromic acid as our intermediate acid etching agent. This is an SEM image of one of these samples after a third anodization at 40 volts. As you can see, these pores are highly ordered both vertically and horizontally, and this is basically exactly what you would be looking for. Again, this is the same sample except much closer at a much better scale, and we were able to measure the diameters of these pores roughly, and we were able to calculate that the average pore size is 45 nanometers, which indicates to us that the pore size is proportional to the anodization voltage. So the next step after having these highly ordered pores is we want to reduce the barrier layer. We did two different things to reduce the barrier layer. One was we implemented a voltage drop, which is indicated by this red line after the third voltage. So we would lower the voltage from 40 volts to 10 volts with a step size of half a volt for roughly 20 minutes. What this does is it is indicated here by the blue line, which is the current response during a voltage drop, is it basically disturbs the equilibrium of the oxidation reduction reaction that is occurring, causing the oxide to be consumed during the reaction. So I'm just going to go into optimizing the barrier layer thinning. At first we did a 10-minute voltage drop and then an acid etching for 10 minutes using 0.1 molar phosphoric acid, and we took it to the SEM and we found that we did increase the pore size on average without removing the entire oxide layer and removing all the pores. Average pore size was around 50 to 55 nanometers. So we decided that we were going in the right direction, so we thought, why not increase the voltage drop? So we went from a 10-minute voltage drop to a 20-minute voltage drop while still keeping that 10-minute acid etching. And again, the pore sizes did increase as well without losing order again. So we were able to go up to about a 62 to 68 nanometer average, which we were really happy with considering we started around 40 to 45. This is just a slide to show an example of the reproducibility of these samples. So we created another one doing another 20-minute voltage drop and a 10-minute acid etching, and the pore size is on average 62 nanometers again. So after we were able to recreate these highly ordered, thinned out samples, we wanted to use a pulsed alternating current to electrodeposit nickel into these pores. We used a solution containing boric acid, nickel chloride hexahydrate, and nickel sulfate hexahydrate, which is essentially just an electrolyte with very high nickel concentration. After we had inserted these nickel wires, we want to take these samples to the vibrating sample magnetometer that Zach worked on to see if we can see any hysteresis. If we can generate hysteresis curves, we will be able to tell different magnetic properties of our samples, such as the saturation magnetization and the coercivity. This is an example of our first sample, or this is an image of our first sample after using this pulsed signal to apply to the electrolyte. It was a pulse signal that went to negative 10 volts for roughly 80 milliseconds, and then it jumps up to 3 volts for roughly 20 milliseconds, and then we had a second off time of 0 volts. This is the surface. It seems quite reflective after the deposition, so we decided to take it to the SEM and look at the surface. What we determined is that we had basically completely covered the surface of the substrate with like a nickel plating, essentially, and that's indicative of like these little specks that were on the surface. And also, if we tried to go and find the pores at a higher magnification, they were just gone. You could not see them. So what we decided to do to see if we still had, if the pores were still really there, if we had ruined the sample during this process, is we cut the sample in half and we took a cross-sectional image, which is this image on the right. As you can see, there's still these vertical channels that are pretty symmetric and spaced apart, which is indicating to us that these tubes created by the nanopores are still residing in the sample. However, when we tried to look to see if there's any nickel inside, it's pretty inconclusive and not very accurate to say that we can see nickel inside these nanopores. So we decided to revise the pulse signal that we sent to our sample because obviously we had deposited too much nickel and covered the entire surface. We decided to keep going with a negative 10 volt to 3 volt kind of pulse signal, but on the previous signal, I forgot to mention, we used 2 DC power supplies in series to generate that pulse. Those DC power supplies weren't able to switch the voltages or really do it at a short enough pulse. So what we needed to do is we used 2 function generators in parallel actually with our sample, and we were able to create the same voltage pulse from negative 10 to 3, but this time this negative 10 volt signal is only for 8 milliseconds and the 3 volt signal is only for 2 milliseconds. So we were able to reduce the time of this pulse by 10 times. And so after we had done this deposition, we took the sample to the SEM to see if we could still see the pores, and we could, which is a really good thing, which indicates to us that we potentially did the electrodeposition and deposit these nickel nanowires without filling up the surface of the sample. And also, we did some measurements to make sure that we weren't like closing up the gaps of the pores as we deposited too, and the average is still around 60 to 65 nanometers, which is good. So after we had done this, we felt pretty confident that maybe we had some nickel nanowires inside these samples, so we decided to take this specific sample over to the VSM and run a hysteresis curve of it. Unfortunately, the hysteresis loop was inconclusive, as the data was very noisy, as you can tell, potentially indicating that the nanowires are just too short, meaning that in future work, we will want to use the same parameters as this last sample, sample number 2, but we believe longer durations of a pulse will help reduce the noise by growing longer nickel nanowires. The curve over here, as you can see, it's not very good, but there is some vague symmetry going from the bottom left to the top right, which we're hoping if we can grow longer nickel nanowires that it'll clean up all this mess in between. I'd like to give acknowledgements to Steve Anderson for being very helpful in all his technical support. I'd also like to thank the chemistry department and chemistry stockroom for help on producing several different acidic solutions such as the chromic acid. I'd also like to thank the Corette Scholars Foundation for providing funding this semester to continue the research. And I'd also like to thank the Hitchwas for their Hitchwa Summer Scholarship, which helped get this research started over the previous summer. And I'd also like to give a special thanks to Dr. Shi for his guidance and assistance on this project.